letting me speak today. And thank you everybody for being here. Today I'll be presenting a neutron gamma coincidence experiment done at Florida State University in order to understand the peak gamma reaction rate in astrophysical environments which populate low-lying proton resonance states in 26 silicon. First, I'll be going over the relevance of this reaction and its influence in galactic aluminum-26. I'll go over some of the recent work done over the past couple of years to try to understand this peak gamma reaction. Since this experiment used the CATRiNA array, which is a detector I've used extensively throughout my PhD career, I'll go over some of its functions. Finally, I'll go over the experimental details and I'll present some preliminary results that seem quite promising, finally summarizing and my acknowledgements. Nuclear astrophysics seeks to understand how nuclei are produced and destroyed across the universe. Light elements such as up to lithium were created during Big Bang nucleosynthesis, and heavier elements created in stellar processes such as novae and supernovae. Here on the right, I show a table of nuclei where the y-axis is the number of protons, x-axis is number of neutrons, and we try to understand how stable nuclei, which are shown in black, are created in a galaxy and how these any short-lived nuclei may have any influence in overall abundance. One of the uncertainties in the studies is the uncertainties in reaction rates, the masses of these nuclei, and their structure. And nuclear physics can help in this issue by measuring these properties in a laboratory. The first sign of ongoing nucleosynthesis in our galaxy was by the detection of aluminum-26 decay. Aluminum-26 decay has a half-life of 700,000 years, which decays to magnesium, releasing this 1.8 MeV gamma. Since its lifetime is much shorter than the galaxy's age, its ongoing detection gives evidence of ongoing nuclear synthesis, which provides a pretty important link between the astrophysical phenomena which this element is created in and the nuclear physical properties within. Here, the distribution is shown for the aluminum-26 decay, and it shows that its concentration, it gives indication that it probably a large portion comes from massive stars and their subsequent supernovas. But there seems to be some possible contributions from novae. The overabundance of magnesium-26 seen in meteorites can be explained by this addition of radioactive aluminum-26 as these meteorites pass through the remnants of these explosions. One issue in this picture is the introduction of a low-lying isomer in aluminum-26, which can beta decay straight to the ground state of a magnesium-26, bypassing this 1.8 MeV gamma. So if one seeks to understand if one seeks to calibrate what one observes in the sky with what's seen in the meteorites, one needs to fully understand in these environments how the isomer may contribute to the overall abundance of aluminum-26 ground state, sorry. The production of both of these isomers, these isotopes are, this nuclei branches off aluminum-25. It could either proton capture up to 26 silicon, then beta decay down to the isomer, or aluminum-25 could beta decay to 25 magnesium, and proton capture, which primarily populates the ground state of aluminum-26. So therefore, one needs to understand what is the proton capture rate and see if it competes with the beta decay of aluminum-25. How does one do this? Well, one needs to calculate what's known as the reaction rate per particle pair, which is given here on the down left. What's important here is to know that the half-life for proton capture is inversely proportional to the reaction rate. So therefore, by calculating the reaction rate, one can see if this proton capture competes with the beta decay of aluminum-25, which is about 7 seconds. So what does one need to obtain in order to do these computations? Well, one needs to identify the resonance state, which mostly contributes to the reaction rate, the partial widths of the state, and the J pi. Here on the right, I show what's called the gamma window, which is a product of the Maxwell distribution as well as the tunnel probability in these environments. Well, within this gamma window, one can see which states contributes the most to this reaction rate. So one simply needs to identify these parameters. The problem in all of this is that studying the peak gamma reaction is quite difficult, since one needs to use one would have to use a radioactive beam along with gamma detectors, which have relative low efficiencies when compared to other types. So surrogate reactions have been used, such as DN, helium-3n, and PT reactions to try to understand or populate these low-lying resonance states and see what are the parameters or what are their properties. For states unobserved, unfortunately, we've relied on models we've relied on models that rely on theoretical predictions in order to see where these energy levels are and what are their JPIs. First, I'll go through what the theory tells us and then I'll follow up with what the experiments have shown us. From the show model calculations and mirror symmetry assignments, one expects 4 resonances within the gamma window. We see a 1+, 0+, a 3+, and a 4+, and as well as their theoretical and some experimental partial widths. So here, if we notice that the exponential term is the resonance energy, it is very important to locate these states as is the strongest influence in the reaction rate. Additionally, one needs to obtain the partial widths of this state as given here, and as one can see from this plot in theoretical predictions, one expects the 3+ to have the highest contribution. So it's important to locate this 3+ correctly, and as well as its energy level. So what has the experiment tell us? In 2016, there was a review which pretty much summarized the work done on 26 silicon, in particular in the low-lying states within the gamma window. The 4+ was first identified just about 0.04 MeV above the threshold. And as you can see here, it will not contribute significantly to the reaction rate. Therefore, one then looks at 3 possible states that can contribute. The next one, the 1+, was identified at 5675 by a 3 helium-6 experiment, and it was confirmed thereafter by many others. Now, the 0+ was recently confirmed at 5.89 by an experiment done at Argonne, which places this guy at 5.89 with a 0+ JPi. So that leaves possibly one state left, which is the 3+ that I discussed before. In this state was identified by a helium-3n, a DN, and a PT study. And the first decay from this state, the gamma decay, was observed by a beta decay experiment in 2013 done at NSEL, where we identified the 3+3 to go into the second 3+ by a 1741 keV gamma emission. Here on the right, we see their on the left is their beta gamma coincidence spectrum, and here they see a state around 1740, which they identified to be the 3+. After a beta gamma gamma coincidence, they see a couple of counts down here, but one expects very low counts for this state, as it's about 1.5% benching ratio. And another experiment in 2017 tried to see this transition using the helium-3n gamma, but unfortunately, due to the low branching, the background was a lot higher than the expected counts. Therefore, it was proposed that reducing the background may be a way to identify this, to see this transition. There's another state that has been observed by a couple of experiments. The helium-3n, one of the 3 helium-3n experiments that identified the 3+, also identified a state at 5.95 and assigned it a 0+ parity, 0+ JPi. Another experiment in 2010, which was a PT experiment, populated both the 5.92 and the 5.95 state, but populated it weakly, so they were not able to assign any JPi. So both of these states see both of these, both the 5.92 and the 0+ state at 5.95, but they don't see any 0+ at 5.89. The other experiments, which did helium-3n as well, should populate this 5.95 since they ran at similar energies, but they have identified the 0+ at 5.89, and they don't see any state at 5.95, which leads to the question, what did this experiment exactly see at 5.95? And if it does it exist or does it not? And if it does exist, what is its spin and parity? One of the explanations could be that there was a possible calibration issue due to them using an old silicon-26 mass, which may explain a shift to the right way, in the right direction in terms of energy level, but it's uncertain that that was the case. So we proposed of running this experiment at Florida State University. This experiment will be done using a helium-3N reaction to study these low-lying proton resonance states. And the goal was to use the same reaction that observed the 3+ and the 0+ at 5.95 to see if we can see the 0+ at somewhere in that region and compared to what was previously reported. The neutrons will be detected by the CATRiNA detector, which will provide PSD, pulsar data alongside the time of flight. The gammas will then will be detected using the FSU highly purified germanium detectors, which will also bring in the resolution in order to see these states. Again, the goal is to confirm this transition reported by a beta decay experiment, where they saw 1741 gamma emission with a very low branching ratio, as well as provide additional data on the 0+ state observed at 5.95 using the same reaction. First, I will introduce CATRiNA before I go into the experiment. Our idea of using CATRiNA for this experiment came from some of the attributes that have been reported in their pulsar data, which shows a significant peak, which could be attributed to 1/8 of the incident energy. Typically, neutron spectroscopy has been done using time-of-flight information, where one places a detector some distance away from their target, and using time-of-flight, they can extract neutron energy. On the other hand, deuterated scintillators, like the ones used at Triumph using the discount detector, have shown great time-of-flight capabilities, but also this pulsar peak in their pulsar spectrum. This is not observed in hydrogen-based detectors, which I show here in blue, as their scattering cross-section is quite flat compared to the asymmetric cross-section for neutron deuteron scattering. So we got a couple of these at Florida State University, 16 from Elgin Technology, and I was tasked with characterizing them and developing them in order for us to be used for this experiment. And the way that they work is essentially that the scintillator material is within an aluminum capsule, as I show here. It's coupled to a photomultiplier tube using optical guide, and we pick up their anode signal, which typical signal I show here. For gamma events, the decay is much faster than the neutron events. So using different integration times, one can use these values to differentiate between their neutron and gamma signals. Using a light output unit known as KVEE, we set a threshold at 250, and where one can then project to the x-axis to obtain what's known as a figure of merit. A figure of merit over 1 lets you know that you have pretty good separation between both of these events. Here, a figure of merit of 1.3 is obtained at that 250 kVEE. At the moment, these 16 detectors are placed in a configuration as I show here, where they cover a total of about 80 degrees of angular coverage. And while they used to be, the data acquisition was done with analog electronics, I've upgraded these guys to digitizers using kind 1725. We characterize these detectors using a PN reaction on a 7 lithium target, where we essentially try to populate the ground state of 7 beryllium to produce quasi-monoenergetic neutrons. As we increase the proton beam, we see this neutrons in the top slowly shift to the right as you increase proton energy. And of course, the neutron energy increases as what's written here. If we gate on these neutrons and then project down to my long gate value, I indeed see a peak that shifts to the right as you increase neutron energy. Using this information, I then obtain what's known as a light output curve, which essentially lets you know what is the relationship between my light output units and the energy deposited. Again, remember the energy deposited is just 1/8 of the incident energy, so one can essentially extract neutron energy from this plot. Additionally, I use this plot here in order to plot my efficiencies obtained from this experiment versus my MCNP simulations, where I essentially use the energy deposit information in my simulation to convert to KEVEEs, and then vary to see what will be my the efficiency, which is threshold dependent, and how it varies. As you can see, we have pretty good agreement between the efficiencies of the detectors and that obtained from the simulation. As well, and additionally, I as well obtained the resolution curve, which is necessary in order to build what's known as the response matrix. Here, I show the response mixtures on the left, which essentially lets you know what is the response of the detector over an energy range, which I did from 100 keV to 12 MeV. Using this information, we were able to build an algorithm which essentially unfolds this light output spectrum and gives you what is the probability of those neutron energies given the light output that you give it. So essentially, given the light output, what is the X or what is the neutron energy? Simply one on where R is my response matrix. One simply finds the inverse of this function to obtain their energy spectrum. As you can see here, our unfolded neutron energy seems to agree quite well with what we obtained from the time of flight information, which are right here on the top. While this is great, we wanted to see how this unfolding did with a more complex light output spectrum, which obtained more than just one peak. For this, we did a DN experiment at Florida State using a CD2 target, and we also moved the scattering chamber for the detector over to the other side of the hull, where we put a new scattering chamber in order to reduce any background from neutron scattering. Additionally, we extended the beamline to reduce any beam-induced background from any neutrons or gammas coming from the beam side. We see the CATRiNA detectors sitting 1 meter from the target, where I then use time of flight information and pulse height data to extract neutron energy. So here I plot pulse height versus time of flight. And as you can see, the neutrons with the shortest time of flight on the left have the highest pulse height value. Projecting my y-axis, we indeed see a couple of peaks here, which could be attributed to several states, where in the time of flight information, we can observe which states they are, three helium ground state, and a couple of states in 13 nitrogen, two of them being resonance. So how does that compare to our time of flight? Where after unfolding, this four peak pulse height, we did see a good agreement between our time of flight energy and our pulse height unfolding energy. The pulse height algorithm is still in the early works. There's a couple of improvements we can do, which is the response matrix itself. So for the analysis that I was about to show, the unfolding wasn't used, but using pulse height data, we can clean up our spectrum a lot more. So again, I bring it back to this Helium-3N experiment that we did here at Florida State, and remind everybody what was the goal. The neutrons will be detected with CATRiNA, and the gammas will be coming from the FSU clovers. And the goal again is to see the 1741 keV gamma with a 1% branching ratio, and possibly give more information on this 0+ state, which was observed using the same reaction. So we ran a 10 MeV stable beam of Helium-3, with about 10 nanoamps at target, with a self-sustained 24 magnesium target. We had about 82.5 nanosecond bunching with 1.7 nanosecond resolution, and our beam line was extended 2 meters downstream in order to dump the beam into a graphite piece, which was then surrounded with borated polyethylene to again reduce any beam-induced background. We ran a total of about 2 weeks with 1.5 terabytes of data, and we had a total of 16 CATRiNA detectors 1 meter from the target, with 3 FSU clovers placed at 90 degrees, and 2 singles, 1 at 90 degrees and 1 at backwards angles. For the data acquisition, I coupled these detectors using a times 1725 digitizer. These digitizers have a 4 nanosecond sampling time, and it pretty much provide you with every event energy, the short if you're using PSD firmware, their channel, and the timestamp. The analysis for the event builder using these digitizers was built from scratch here at Florida State. So as you will see, it's still a work in progress, but the results that we've seen so far are pretty promising. We used a total of 5 boards, 3 of them using PHA software, 2 of them using PSD, where 3 clovers were on one board, 2 singles on another board, 3 of my BGOs on another one, my RF on a PSD board, and finally the CATRiNA boards on the last one. The reason this was done like this is because a stop is given to the master that is daisy chained all the way down to the last board, where the trigger output now is free for the last board. I can mask this trigger output to give me a signal whenever the CATRiNA boards fire, or the CATRiNA detectors fire, sorry. And I put that in with an AND logic where an RF signal in coincidence with any of the CATRiNA detectors is then given to a board, the RF board, as a channel. The reason you need to do this is because the RF comes in at 6 megahertz, which would pretty much destroy your board if you just took it in as is. So one has to essentially only provide an RF signal whenever any of the detectors fire only. Additionally, you have to smooth the signal out since the rise time is much faster than the sampling time of the detectors. So one needs to generate a gate which is wide enough for the signals for the boards to give you a proper trigger. The FSU clovers have never been used using the kind digitizer, so I was also tasked with implementing them into this system. The FSU clovers are pretty much 4 crystals per clover, which give you add-back capability as well as content suppression capabilities due to their BGO shield surrounding them. You can either have events where one comes from the left top, hit one of the detectors, give part of its energy, and then go to another detector. But using my event builder, I could go in and just add this back to give me the full energy of the gamma. Or I could veto events where one comes in, gives partial energy, and then comes back out. I tested this first using a couple of sources. Here I show an example using the 60 cobalt source, and I was able to get a resolution that was comparable to the XI60 system, which is the one that is currently used at Florida State University. So here's a typical time of flight spectrum for a neutron detector. Here on the top right, I show the ungated time of flight spectrum, where I identify my prompt gamma peak and place it at 3 nanoseconds. I then gate on my neutrons, as I show here on the left, where I apply then this gate to my time of flight spectrum to get a very clean neutron time of flight spectrum. Then using this time of flight, we can start identifying a couple of states, as I show here on the left. First, we see the ground states, and a couple of states thereafter. I've identified the time of flight for proton separation. Anything to the right will be resonance. We see some 16 oxygen contribution, and that's because our target does oxidize, and unfortunately, there's no way of escaping this. So it isn't within our spectrums, but thankfully, it's out of our time of flight of interest. Using 1/2 mv squared, because we're non-relativistic speeds, I then use the detector angle and neutron energy to do a reconstructed Q value for all of my detectors, as I show here on the right. Since the Q value for the ground state is just 70 keV, one can read this as the negative of the excitation energy of the state. Here I marked the separation energy at about 5.5, and anything to the left will be resonance. As you can see, the resolution doesn't come from our neutron detectors, it will come from our gamma detectors. And this is shown here, where my y-axis is my Q value, and any gammas that came in coincidence with my neutrons are shown on the x-axis in keVs. Since I've yet to correct for any Doppler corrections, only show the 90-degree detectors here. And to give you an idea how one will read this plot, here I've identified a couple of strong transitions. We see the second 2+ going to the first 2+ here by almost 1,000 or 900 MeV. Sorry, 900 keV gamma, as I show here, or 988, as well as the two other 287 going, the first 2+ going to the ground state by 2787 emission, as I show here. And the reason that you see it across the map is because you see a lot of states decaying to these, feeding these states when they decay. But as you can see here, one can kind of see that this guy is pretty much around the region where it needs to be, which is around 2.7 Q value. To better illustrate this, let me go to this high energy gamma here. This high energy gamma seems to agree quite well with what was reported for a 2+ transition going to the 0+ to the ground state by an emission of 4141 keV. Therefore, if we see this 4141, we should also see the 2341 around the same region. And indeed we do, there it is, with a 23, almost 2350 keV gamma. So now for the region of interest, which is the resonance energies, resonance state, sorry, I'll zoom in here to the bottom right. from the bottom from the left to the right, we see a couple of gammas here. One at 3100, which seems to agree with this 0 plus transition coming from this state going to the second 2 plus. In the middle, we actually see the 1 plus going to the 2 plus by an emission of 3878 keV gamma. And lastly, we see another transition from the 0 plus going to the first 2 plus by an emission of almost 4100 keV. If it wasn't for the gamma detectors, we will not be able to distinguish these two different states. But as you can see, there's a slight shift just up from these two states here, signifying that these are two different states that were populating. Now, how can we use our Q value? Well, if I gate here on this gamma and project down to my Q value, one sees a centroid around 5.83. If one remembers, one simply needs to add about 70 keV to this to give you the actual excitation energy. So it seems to agree quite well what's reported for the 0 plus transition. Now, what does the neutron gate tell us on the gammas? Well, if one were to gate on the 5.9, what gammas do we see? Well, if one starts looking around the 1740 region, which again, remember, was reported by the beta decay experiment. If one starts looking at the 1740 region, just to the left, we again see this oxygen contaminant in the form of 18 neon decay. Just to the right, we see another 0 plus transition, this one being the 1751. And just at 1740, we see some structure which seems to agree quite well with what was reported before for the 1741 keV gamma transition. But I still need to improve this analysis a little better, and this will be done by first reducing my background, which I've yet to do in terms of Compton suppression. I will simply veto on the timestamps given by the BGO, as well as post-high gating, which I can go over a little later if anybody's interested, as well as improve my statistics by either Doppler correction or, by Doppler correction. That way I can finally add that backward angles detector. In summary, I characterized and developed the CATRiNA array at Florida State using source test Monte Carlo simulations in a 7/8 NPN reaction. Using this information, we built a response matrix for the detector, which will be used later for my analysis to see what kind of information we can extract from that light up spectrum. I coupled the CATRiNA array with a gamma ray detector for a neutron gamma coincidence experiment. And we saw a couple of low-lying proton resonance states in 26 silicon, where I identified 3 transitions previously reported for the 0 plus. And I placed this state at around 5.9, which agrees quite well with the helium-3 gamma experiments previously done, and possible evidence for this 3+3 going to the second 3 plus by a 1740 keV transition. I still have some work to do in terms of analysis. Since this is built from scratch, I hope you can forgive me for not being a little later on stages in terms of the analysis, but all I need to really introduce is the BGO rejection, post-high gating, and finally correct for any Doppler effects. I would like to thank the NNSA for funding the CATRiNA array and funding me, the NSF for granting the lab that I work in, and my advisor and research group who's helped me tremendously. The person that wrote the unfolding algorithm was Ashley Morlock, so big thanks to her, and everybody at the John D. Fox Laboratory who has helped me tremendously. And thank you all for listening.
Okay. Thank you very much for this very nice presentation.
Thank you.
Now we have time for questions. We have 2 Daniels that raised their hand, so I will start with my office neighbor, Daniel Bardayan.
All right, thank you for that very nice talk. It looks like some really interesting work, and you have lots of data to look through, it looks like. Do you think, this 5945 keV state that was seen by Perpadas seems to have rather tenuous evidence for its existence? Do you think you'll be able to say anything about whether it exists or you see it or anything about its properties?
So far, I've yet to see anything really in that region. But by that I mean I've yet to see any states just below, just below the 5.9 Q value. And if I were to see, if there were to be anything there, it couldn't be the 0 plus. So it may either be a negative parity state or a high spin state that I don't think we may be able to populate. I know that they ran at the same energy with the same reaction, but so far I have not seen anything around that region. But maybe with the cleanup, perhaps I can see something, since it might be something that has very small branching ratio, perhaps I can see it once I finally do my cleanup. But at the moment, I can't say that I for sure see something around 5.95 as to, or to why I don't see it.
All right, thank you.
You're welcome.
Okay. And the second Daniel.
Hey, Daniel.
What is up, Jesus?
Hope you're well, man.
Thank you so much for talking to us about your work. One question I had, being a mass guy, you said something that was a little interesting to me, and I wanted to ask for a little more clarification on. You said that there were some issues, this was toward the beginning of your presentation, with the silicon 26 mass.
Yeah.
But a quick lookup shows that it has it's known down to a precision of 100 eV. Could you clarify a little bit more on what you mean by?
Yeah. So hopefully somebody will correct me if I'm wrong, but I think that study was done in 2002 or 2004, and the mass has been updated since then. So you're right. No, we know it very well now, but at that time when that was reported, it wasn't that. It wasn't like that. So there's been there, of course, no problem.
Okay.
It has actually changed by 6 keV since the Ohio University experiment was analyzed. So that was a quite significant shift. And it wasn't clear how strongly that would have affected their calibration, but it is significant.
Thank you, Ingo.
Erin.
Hey, Jesus, nice talk.
Hey, Erin, thank you.
I was just a little curious about your DAC, obviously. Did you end up using Compass or NSDL DAC? How did you get that to work?
Yeah, I use Compass. I think Sudarshan is still, I haven't heard any news on the NSDL DAC part. But yeah, we used Compass, and thankfully everything worked out great. But no issues with Compass on our end.
Yeah. Did you end up using an event builder code similar to the SPS one?
Yeah, so I pretty much took the SPS code and reworked it to what I needed, a little more user specific.
Sweet.
But the whole grabbing the binaries and that's still the same, but the analysis part, the logic part, are completely different.
Yeah, I figured you might have done something like that. Just curious. Thank you.
Yeah, thank you.
Kelly.
Hey, well, I was just wondering, because you didn't spend too much time on it, if you could go into a bit more detail about your spectrum unfolding, measurement of the response matrices for these detectors, and how
do I intend to use them, or where are we at now with that?
I guess, yeah, like where you're at now, what has been done already in terms of characterizing those detectors and getting the response matrices.
So yeah, I didn't show it here, but we were able to obtain a cross-section, angular cross-section for these guys using the unfolding versus time of flight, and they actually agree quite well. But one of the things that we really want to narrow down is the errors in our approach for unfolding. And the algorithm itself could have errors, and one of the largest attributes is actually the response matrix itself, since I had to simulate it. So we're actually going to go to Ohio using their neutron tunnel to do an empirical response matrix, which would improve our results a lot. And in terms of how I will use it for this experiment, I actually have a backup slide. I didn't want to get too much into it because it's still the early stages of how I'm using it. But the way that this will work essentially is that I will plot time of flight versus my pulse height, and essentially try to narrow down on the region that I know these neutron energies are. So again, using this light output curve, I know that my neutron energies are around 3.5, which will be an energy deposit of around 3. So you see, if I can narrow down at around 800 keV, which will be around, let's say here, for my neutron interest, I could clean up my data tremendously. But now you're fighting statistics because you're throwing away a lot of events that could possibly be your neutron. So this is kind of the game that you play with this pulsar data. But in terms of unfolding, one way that you could use it is that you could either gate on a gamma and then go to your light output spectrum and then unfold that to see which neutrons came with those gammas, for example.
Sounds like you've got a lot of data to play with.
And the other graduate students. But yeah.
Okay, any other questions? Philip.
Hello, can you hear me?
Yes.
Great. I have what's possibly a rather naive question, but you're using helium-3n, which I think in the past has often been used for pair transfer, and that typically favors natural parity states. But here you're looking for a 3+ state, which is not a natural parity state. Is that a concern, or is it not a pair transfer in this case?
The reason we so yeah, that's a great question, and the reason that we wanted to go ahead with this was since Parpotas was able to identify the 3+ and populated enough to identify the 3+, we expected to see that as well as possibly the 5.95 it does exist. So we're kind of trying to do both at the same time. But you're right. If you in this kind of ideal reaction would be kind of like a DN, like with 25 aluminum, but then you're fighting again the game of radioactive beam with a gamma detector if you're trying to see the transitions.
Oh, okay, cool. Thanks.
You're welcome.
Romualdo. Romualdo, you're muted, so we can't hear you.
Very nice talk, Jesus.
Thank you.
The question I was wondering is, you mentioned using pulse height to reduce your background further. Can you make an estimate of how much that would help you without actually doing all the work?
No, I couldn't tell you at the top of my head, honestly, Romualdo. That's something I haven't really explored, and since the only really use that we did the time of flight versus the pulse height was with this DN with the CT2 target, and that was very clean. There wasn't any other influence, meaning any closed states. Everything was very well separated. So in this case, I couldn't really tell you how much, since a lot of these neutron energies will be overlapping on top of each other. So it's quite difficult to do with so many states in there to give you an idea of how much it'll fix it up. Definitely the strongest contributor in terms of cleaning up background will come from the BGO rejection, not the pulse height. But pulse height would definitely help, at least reducing any neutron background or low energy neutrons.
All right, thanks.
You're welcome.
Okay, I don't see any other raised hands. Last chance for questions.
Going once.
Yeah. Okay, if there are no more questions, thank you all for joining. Thank you, Jesus, for this great presentation. And we have 2 more seminars till the end of the semester. So I encourage you to check out the website and join us in 2 weeks. Thank you very much.
Thank you, everyone.